Okay, thank you very much to James and to the people at the Centre for inviting me to give this talk. I should start by apologising for getting the name of the Centre wrong on my slide. It's the Centre for Science and Philosophy, not the Centre for Philosophy and Science. That's not a subversive attempt to increase the importance of philosophy. It's just an absent-minded philosopher's mistake. Okay, so what I want to talk about today is about the role of philosophy of physics in helping form and understand a theory of quantum gravity. I think that's kind of an interesting topic because I think that the role here is a little bit different from the one that philosophy of physics is perhaps playing in other areas of fairly established physics. I think there's genuinely a role that philosophy of physics can play here in actually forming the theory in itself and in particularly helping us to understand the empirical content of these kinds of theories. But that might be all going a bit fast. I mean, lots of you might not even know what philosophy of physics is. So what is philosophy of physics? Well, philosophy of physics in its broadest sense examines the conceptual and interpretational problems that arise in physics. There are a great many of these, but I'm going to put things into very inaccurate boxes by saying that there are, roughly speaking, three kinds of divisions in philosophy of physics. Whenever you say this kind of thing, you're bound to offend some of your colleagues by not including what they do in the umbrella, but I'll plow ahead anyway. So, firstly, we have quantum theory, quantum mechanics, quantum field theory. Secondly, space-time physics. Thirdly, a very broad umbrella group that I'm going to call inter-theoretic relations. That's particularly thermodynamics and statistical mechanics. There's a lot of work on that, but you'll see that there's a little more than that. Now, I'm going to briefly talk about all three of those things, because although I want to focus on the role that philosophy of physics can play in the development of new physics, namely quantum gravity, I think it's quite interesting that some of the problems that philosophers have been addressing in those three areas are actually relevant to the problem of quantum gravity, and hopefully I'll convince you at least that that's the case. So let's start with quantum theory. Well, it's an oversimplification, but not a gross oversimplification, to say that most philosophical work on quantum field theory, or quantum field theory perhaps, deals in some way with the superpositions involved in the theory. So quantum mechanics has this strange feature. It has this feature that if you take one solution to the equations and you take another solution to the equations, then a superposition of those two solutions is also a solution to the equations. Roughly speaking, that means that microsystems can be in something like multiple states simultaneously. That's obviously a very puzzling thing to understand. And understanding how we should think about the properties of microsystems is a lot of the work of the philosopher of quantum mechanics. Perhaps even more worryingly, there's this question of why we don't see these same superpositions, these same multiple states at the same time in macroscopic systems. And that's the famous problem of Schrödinger's cat. That's why there's a cat in a superposition state of alive and dead on the slide. Finally, there are questions about how we should understand the probabilistic nature of the theory. Okay, so there's a whistle-stop tour of philosophy of quantum mechanics. On to whistle-stop tour of space-time physics and philosophy. Now, philosophical work in space-time physics is mostly an attempt to understand the kind of curved, unified space-time that general relativity postulates. General relativity is our best theory of gravity. It says that space-time curves dynamically in response to matter. So gravity, rather than being a force, turns out to be an aspect of space-time geometry. There are lots of problems for traditional philosophy that this throws up. For one thing, we're working with space-time, not space and time, and we need to understand how we get back kind of traditional ideas about space and time and how they're affected by this unified space-time. But we also need to understand what it means for a dynamical field to represent space-time, because what's happened is rather than space-time being this fixed background container, we've turned into something that responds to the presence of matter, that's a dynamical field much like our other force fields, for example. And finally, philosophy of general relativity tends to be quite forward-looking, because I think people who work in general relativity are perhaps more aware, if anything, than people elsewhere, that GR is not the be-all and end-all, it's not the final theory. We know that this theory can't be quite right. We know we need a quantum theory of gravity. So we want to know what the distinctive features of general relativity are that have made it so successful that should be carried forward to future theories. What's the kind of big conceptual change that we need to hang on to in future theories? Finally, and here's my very broad umbrella under which I sweep a lot of kind of messy work, but good messy work in philosophy of physics, into theoretic relations, thermal physics, and philosophy. So this more disparate topic concerns how you can understand relations between theories. And the particularly interesting relations between theories are between theories that describe robust, interesting, large-scale behavior, and theories that describe microphysics of the same kinds of systems. So we want to understand how, say, a theory like thermodynamics, which describes features that we know that the micro world doesn't have in any distinct sense, like temperature, their large aggregate properties, how that relates to a micro description. So lots of these examples are in that intersection between statistical mechanics and thermodynamics. Phase transitions are particularly interesting. That's why you've got boiling water up there, water undergoing a phase transition. There's certain puzzles that arise when we try and understand that, both from the thermodynamic side and the statistical mechanics side. It turns out it's quite a complicated relationship between the two theories in the case of phase transitions. Under this same umbrella, though, I'm talking about problems that try to understand how, say, continuous descriptions arise from discrete microphysics. So if we want to do fluid mechanics, we need to pretend that a system's continuous, but we know that's not the real story. We know that there's a molecular description that's a discrete description underneath. And very generally, these kinds of ideas about deriving macroscopic structures from microscopic structures involve something like a high degree of approximation and idealization. And what we need to understand is in what circumstances these lead to robust phenomena, when these lead to kind of appropriate higher level behavior. And that's to some degree approximation and idealization, and the nature of those are very much a kind of philosophy of science topic. So there's work for philosophers here. Okay, so that's the very quick tour of a lot of physics and most of philosophy of physics. What about quantum gravity? Well, why do we need a theory of quantum gravity? Well, we don't know how to model gravitational force in quantum mechanics, nor do we know how to do quantum mechanics in a dynamical curved space-time. So our best theory of gravity and our best theory of everything else are at odds, and it turns out that combining them is a very tricky business. To see in the roughest possible strokes, throwing huge amounts of complexity under the carpet, why that's a tough task, just think about two of the things I've already said. General relativity posits a curved dynamical space-time. So remember, this space-time, it's part of our dynamics. It's not this fixed background that everything plays out on. But quantum theory involves superposition states of dynamical systems on a fixed background space-time. So quantum mechanics says that dynamical systems exist in these superposition states. And you can even just from that incredibly rough sketch see that combining those two is going to be terribly tricky, because what are you meant to do? Are you meant to make the space-time itself go into superposition state? But then what would you say about the rest of your physics if you no longer have a single fixed space-time? As I say, there's a great deal more to the story than that. But it gives you some impression of how conceptually tricky this thing is. And that might make it no surprise that, arguably, we need to do a little bit of work to establish that this really is the case. But all of our theories of quantum gravity require a radical reconceptualization of space-time at the fundamental level. They just don't involve the kind of thing that we're currently used to thinking of as space-time. It looks like the continuous classical space-time that we experiment in and experience is going to have to be a non-fundamental feature of the theory, something that emerges in some kind of limit. So at the very mildest end, quantum gravities involve discrete, not continuous structure at the fundamental level, or many of them do. That discrete structure could be quite a spatiotemporal structure, or it could be something rather different. So at the most extreme end, there are theories of quantum gravity being proposed that have a fundamental structure that doesn't involve anything like spatiotemporal relations, doesn't involve anything like this familiar background of space and time that we're used to operating in physics. Well, what does a theory of that look like? It's all very well to convince you this is a hard task and something crazy is going to happen at the end of it, but I suppose it's worth taking a brief look at what one might mean by a theory that doesn't involve fundamental space-time. So with huge apologies to people who work in this deep and subtle area, I'm going to do a single slide on loop quantum gravity. So loop quantum gravity is one amongst many competing theories of quantum gravity. I wouldn't pretend it's the most successful, but it's quite an interesting one from a kind of conceptual point of view, because it starts from quite a sensible point, which is saying, look, what would happen if we did to the structures in general relativity what we do to all of the other fields and quantize them, put them through a quantization procedure? And the answer is, well, it's hard, and you get out something odd. The result is something that they call a spin network state. Whenever somebody talks about spin network states, you get a diagram like this one. You see something with a load of nodes, some edges, with numbers attached to them. Apparently, this is the fundamental description of space-time. Now, you might think that that graph could somehow, you can kind of picture a way in which it could build up into something like space-time points, spatial points connected by distances, say. I mean, perhaps that's the meaning. This was meant, after all, to be a quantization of the kind of space-time structures in general relativity. But it turns out it's very tricky to read it like that. The edges of those networks, the numbers that are sitting up there, are spins, but they don't have much to do with distance. In particular, if you take two nodes that are close in the spin network structure, there's no suggestion that they correspond to anything like spatially close structures. That's just ruled out by the way that the theory works. There's a kind of bit of spaciness that comes back in because there's a notion of spatial area associated with the spins. But this is a quantum theory, and quantum theories involve superpositions, so typical states of these things are superpositions of spin networks. So our fundamental description of space-time looks something like superpositions of strange networks of rather unspatial states. And I think it's fair to say, in that case, we don't have anything like space-time at the fundamental level. It's fairly obvious, I take it, that for the philosopher, this raises a huge number of conceptual problems. The kind of things that have sprung to people's minds are things like, look, is space-time even the kind of thing that could be non-fundamental? I mean, a traditional metaphysical picture of the world, and I'm saying traditional metaphysical in sort of in inverted commas, because I mean one that's taken on board perhaps the lessons of relativity theory, but it has space-time as this background container for all of the other stuff. It's the arena, in some sense, in which physics plays out, in which everything plays out, including the fundamental stuff. And if space-time is the arena, the background, the container for the fundamental stuff, how can it itself be non-fundamental? If you asked a philosopher how we could tell the difference between physical stuff and other stuff, like maybe mathematical stuff, abstracter, they might tell you that the physical stuff is just the stuff that is in space-time. So you might be worried that we've even lost our handle on what counts as physical in a theory like this. And we might also be worried about working out how we get back to our description in a theory like this. We might be worried about how we find space-time structure in a theory that has none at the fundamental level. So if we think that the first point on here perhaps isn't too worrying, and we think that we can find non-fundamental space-time, we need space-time to be something like temperature. We need to be like thermodynamic properties. It needs to come out in some limit of our theory. If that were the case, we would need to know how to know it when we saw it. What kinds of features do space-time structure have to have cropped up in a kind of emergent limit? Okay, but I would be, although I have a realist bent myself, I would be sympathetic if there were people in the audience who thought, look, at this point, physics as a realist enterprise has really jumped the shark. It was bad enough after quantum mechanics was hard enough to give a realist interpretation of. But at this point, when we're talking about space-time being composed of spin network states, it's really time to be an instrumentalist. It's time not to think that physics is giving us a kind of fundamental description of the metaphysics of reality. So why don't we all be instrumentalists? That sounds like a good way to stop worrying. Let's see how well this physics works. But now a worry rears its head that's a worry for both the realist and the instrumentalist. Is a theory without space-time even empirically coherent? Can we make empirical sense, a consistent set of empirical predictions from a theory like this? And that's a worry that's been posed by several different people. Why won't you have it? Well, one way of explaining it is to follow a physicist called John Bell, who pointed out that empirical science needs what he called local beables. I kind of hate the word beables. I mean, you could, local stuff, local properties, if you like, quantities associated with particular regions of space-time. The idea is that the kind of thing we're going to be able to measure, the kind of thing we're going to be able to experiment upon, is something like a localized property that's somewhere in space and time. We need to know when and where it is, and we need to be able to perform some kind of localized measurement on it in order to get any empirical content out of our theory at all. And certainly I don't think anyone would disagree with that. I don't know how to perform a measurement that's not in space-time. But Tim Maudlin has elevated this into an argument against the coherence of a theory that doesn't have fundamental space-time. And his argument is something like this. Look, if we don't have fundamental space-time, we just don't know how we're going to find the observable local stuff that we're actually going to measure. And in fact, I think Tim Maudlin thinks that it's going to be impossible to find that kind of stuff. And it's the following kind of idea that underpins this. It's, look, if space-time was fundamental, then we can have the picture that we normally think of having of the levels of physics. We can think of the larger stuff being made up of the smaller stuff, being made up of fundamental particles. We know those fundamental particles in space-time, those littlest bits of space-time, they have genuine physical salience, physical relevance. They're the kind of thing that ought to have physical consequences. And we can build up the observable stuff and the predictions out of that fundamental stuff that's got physical significance. If we don't have that strategy, if we can't think of the kind of small-scale local stuff as building up into the big observable stuff, we're just not going to be able to identify the actual consequences of these theories. If that kind of line of reasoning were right, then theories without fundamental space-time wouldn't just be metaphysically tricky, but they'd be impossible to derive empirical content from. So the idea here is that if that was right, it would just be the case that this was a hopeless task. We shouldn't be even trying to construct a theory without fundamental space-time, because you were never going to get empirical predictions out of it. It's of course well known that theories of quantum gravity currently have no empirical predictions, so we can't sort of hand successful empirical predictions to Tim Maudlin to argue against this. So do we have to accept his argument? Is it the case that theories without fundamental space-time are empirically incoherent? I think the answer is a qualified no. Good news for the quantum gravity project. At least I think the answer is there's no a priori reason in the absence of understanding the details of the theory to think that any of these theories are going to be empirically incoherent. And my reasons for thinking that are roughly the same that are in a paper by Nick Huggett and Chris Wheatrick, which says that, look, somehow this idea that we have to build the big stuff up out of the really small stuff has got things the wrong way round. It's not the case that we have to look at our fundamental theory to work out what has empirical significance and what we can measure and what we can test. We in fact know exactly what's testable. We understand what kinds of quantities we can measure. We know that we can look at tracks in a particle chamber. We know we can measure certain kinds of macroscopic observable phenomena. What we really want to understand is how the physical importance of those kinds of observables filters down to the fundamental level, not a kind of bottom-up picture. And if you think of things like that, then what we need from any theory is just an account of how the theory makes predictions for the stuff that we already know is physically real and observable. All we need is a connection from whatever the fundamental picture is up to the predictable stuff. And yes, that predictable stuff will have to be spatiotemporal. So if that predictable stuff has to be spatiotemporal, then what we really need from a theory of quantum gravity, or one that doesn't postulate fundamental space-time, in order to make it empirically coherent, is an account of how spatiotemporal structure emerges from it. So how somehow, by some crazy procedure of approximation, idealization, etc., we're going to get out structures that look like space-time structures. And the empirical coherence of a theory without fundamental space-time is going to precisely rest on that project. So what kinds of questions would we have to ask if we wanted to know how to identify emergent space-time structure in a theory without any at the fundamental level? Well, there'll be a great many questions to ask, and there'll be a lot of very hard mathematical technical work to be done. And of course, that's exactly what various projects of quantum gravity are trying to do at the moment. But there are also a number of questions that you would have to ask that look something like the following. Look, how can classical space-time states that we don't see in superpositions arise from fundamental superposition states in perhaps the basic description? How can we identify structures that represent phenomenological space-time? By phenomenological space-time, I mean the kind of space-time you and I experience that we do physics experiments in, etc. How do we identify things that play the right kind of role in our theory and have the right kinds of features to counter space-time? So we need to, as I say, know space-time when we see it, when we have performed our mathematical processes and got to the right point. And we need to understand the kinds of approximations and limiting procedures that are acceptable in doing that. What kinds of techniques are okay to use? What kinds of limits can we take? What kinds of idealizations can we use to move from our more fundamental theory to our less fundamental theory? But of course, the first one of those questions was just one of the questions that I brought up under the topic of what philosophers think about when they think about quantum theory. The second one was just one of the questions that I brought up when I talked about what philosophers think about when they think about the philosophy of general relativity. And the third one was the kind of big driving force behind this whole loose area that I said had to do with theoretic relations, things like worrying about the relationship between thermodynamics and statistical mechanics. So interestingly, as perhaps, to this extent, certainly a first for philosophy of physics, it looks like the kinds of questions that we're going to have to ask in this really fundamental area are the kinds of questions that philosophers have already been asking with respect to our current physics. So in conclusion, philosophy of physics has a great deal to offer the quantum gravity project, especially theories of quantum gravity that don't involve fundamental spacetime. It's totally possible to defend these kinds of theories against this charge of empirical incoherence. They can have a coherent set of empirical predictions, but if you want to defend that, you're going to have to involve considerations that are traditionally in the philosopher's domain. And that makes it a particularly exciting area for someone like me, because philosophy has a role to play here, not just in taking some completed formalism and analyzing it, but in shaping the theory and understanding its empirical consequences to begin with. And there are some references in case anyone's curious about further reading. Thank you very much.